Today in class I will do 3.3, and then assuming I don't accidentally lock myself out of the GC again, I will record 4.1 as well and upload that so that before you come to class on Monday, you'll have watched the lecture for 4.1 as well. We got a little bit behind because of the snow day, but now we won't be behind because you'll watch the recording for 4.1. So what are we watching before Monday?
4.1.
Okay. You'll also need to do it anyway because there's homework due on Sunday for 4.1. So unless you want to just not know what's going on, then there's that. 4.1 recording that I'm not covering in person because of the snow day stuff, but you will still have homework due on 4.1 anyway on Sunday. So watch the recording 4.1 before Monday.
Or before you do the homework.
Okay, I'm not supposed to be biased, but this is one of my favorite sections in the entire course. It's very, very fun. In part because it's pretty easy, but it's enjoyable. So let's define some stuff for any n by n matrix. And let's call it A, like we usually do. And any vector B, which has n entries. We're going to let, and this notation is going to be used a lot, so take note of this. A sub I, and then in parentheses, the vector B. Okay, so A sub I of B. That's what we're defining here. This notation is going to be the matrix obtained from taking my matrix A by replacing column I of the original matrix by the vector B. Okay, so what does that mean? That means that essentially my A sub I of B, if I think about listing out the columns as column vectors, I start with my first column, etc., and whenever I get to the ith column, instead of doing A sub I do B. So this would be the ith column of A right here. And then I continue on. Now, granted, any one of these could be the ith column, so you could have the vector B to start, and then all the rest. Or you could have the very last one be the column B, whatever you choose to replace. A more concrete example with numbers in it, in case the abstract one doesn't make the most sense. So say I had some starting matrix A that was 1, 1, 1, 2, 2, 2, 3, 3, 3. Some of you probably just got PTSD. And then the vector B, let's make it 4, 5, 7. Okay. So if I wanted to do A sub 1, so I choose I is equal to 1 of B, what am I really communicating? What I'm communicating is I want to take my matrix A, and I'm going to reproduce the matrix A. But instead of reproducing it exactly, I'm going to look at which column I'm supposed to be replacing. In this case, the first column. And after I replace that first column, what am I replacing it with? Well, the vector inside here, B. So I will replace the first column with this, but everything else is reproduced as is. So I reproduce my matrix, and I am switching out the first column. So instead of using the normal first column, I'm going to put in my vector B. 4, 5, 7, and then proceed as usual with the rest of the matrix. Does that make sense? Okay, so for example, A sub 3 of B would be what? What would the matrix A sub 3 of B be?
1, 1, 2, 2, 4, 5, 7.
Right, so 1, 1, 1, 2, 2, 2. And why are these numbers different, 4, 5, 7?
Because that's the one you replace. replacing.
Yeah, that's the B, and I need to replace this column because of the subscript. Subscript told me which column to replace.
Could you do this with rows?
You technically could, but for the intents of this section, this is the main thing we're focused on right now. It's just replacing the column. So if you want to make up your own definition and start by saying definition for any n by n matrix, blah, 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 you could make language for that. We don't need it on this section, but you could. Okay, so let's now go to Cramer's rule. Cramer's rule. Cramer's rule is really just a name for a theorem, and so in mathematics, named theorems are very important. They're basically theorems that have results that are specifically so applicable that you use it all the time, so that it's useful to actually give it a rule name to reference it by. So let A be an invertible n by n matrix. And by the way, what you don't realize is happening throughout the entirety of this class is this implicit teaching your mind what good thinking looks like. Whenever you study mathematics, it changes the way you view the world, it changes the way you process your thoughts, it changes the way you argue, it even changes the way you write if you let it change you, because math has this really, really strict sense of accountability to correctness that we don't get in the liberal arts. And as much as I love my biblical literature degree and know of the people that would do that, a lot of papers have been published that didn't deserve to be published, for the reason that you're allowed to have opinions that don't need to be true so long as you can make an argument for it. Math says that's a really fantastic false argument. We do not care because it is objectively false, okay? So there is so much, okay? So hold fast to this stuff. I mean, look how precise the language is. That proofwriting language that we talked about in the review, it's every single theorem, every single page of this book. So let it change the way you think, because you will start writing and communicating better with your teams in your work, in the workforce. When you have to write a paper, if you have to make an argument, if you need to convince somebody to do something, you can implicitly pull upon your proofwriting language to make much more compelling and just not false statements, okay? And then you'll catch yourself probably in life making really sloppy assumptions, which you can tighten up because now you're made aware of it, okay? So let it refine the way you think. Let it refine the way you do logic, okay? For any vector B in Rn, the unique solution, and how do I know it's unique? Well, by the invertible matrix theorem of the not vector, this is a matrix equation, AX is equal to B, has entries given by and then we have a formula. So x sub I is given by the determinant of, this is why we needed to learn about the special notation, because we use it here in this formula. A sub I of B divided by the determinant of A. And that's going to be I is 1, 2, etc. for n. Okay, in other words, this is technically a formula to generate solutions of matrix equations. Okay? When you have an invertible n by n matrix, by being invertible, you've guaranteed the existence of your unique solution. And so how to get that and directly compute that? Well, every single xi, so if I want x1 of my solution, I substitute 1 in there. If I want to find my x2 of the solution, I plug 2 in there, so on and so forth. Okay? So it's effectively, Cramer's rule is just a way to hard compute solutions to matrix equations in light of knowing what the determinants are of these. Okay? So this is one that I actually want to prove because the proof is really nice. I think what I'll do, okay, are we happy with this whiteboard over here?
Yeah.
Because I'll erase this and I'll start the proof here and then I'll finish it underneath that.
Throw it away.
Okay. one thing they don't teach in education school is how to organize a limited whiteboard constraint for notes that do not want to fit on your limited whiteboard constraint. Okay. So here's our proof. I do not prove many theorems in classroom time because usually it's not that important. This one's really important, okay? So let's get our ingredients first. We need to have let as a keyword. Here's a matrix A. And we need to know it's n by n and invertible. So we can make it n by n implicitly.
Scott,
Yeah?
is it important as in we should be aware of it or we should know how to do it?
You should be able to reproduce both theorem and proof from hand in Scratch. Mhm. That's implicitly stating the dimensions of my matrix. But I can make it even more explicit. Be an n by n invertible, n by n invertible matrix. I also need to, okay, so this is where some creativity comes in. And this is where the insight's gonna come. So this is non-trivial work. So the first thing is just making sure we're set with the parameters of the theorem itself. This is a non-trivial thing that I would not expect you to be able to generate on your own intuition. So just learn it. E1 through En denote the n by n identity matrix. And then lastly, again, these keywords. If I'm going to be needing to interact with the vectors b and solutions x, I need to just make sure I include that in this list of declaring my variables and such, and make sure we get in the right size. So I need my x and b to be what size? All right, okay. So now we're set, and we can start doing the actual proof work here, okay? So think of this kind of as the preamble. So those dotted lines don't have to exist in your proof, but I'm doing that just so you can visualize the logical kind of flowchart here in the proof. So given the matrix equation, after all, that is the very thing that Cramer's rule is attempting to give a formula for. So we've defined all of our components so that when I write this equation ax equals b, you'll notice that there is nothing that is being used underneath the dotted line that hasn't been given a definition, a place, an explicit callback. So I know what every single one of these components are in their properties because I've made sure to state all of that before I use it, okay? Never use stuff that you have not declared in a proof, okay? That's bad reasoning. So let's show something. So we show that I'm going to multiply the matrix A with this identity matrix sub I of x. This is a non-trivial step. This should not feel obvious, and this should not feel like the intuitive thing as a next step. This is one of those things in math proof writing where you just learn what the trick is and then understand the fallout, okay? So think about applying the definition. Turn back in your notes to when you wrote down the definition for A sub I of B. What that meant was I took the matrix, I'm substituting out the ith column and replacing that ith column with whatever vector appears in this parentheses. So when I'm putting identity sub I of x, what I'm doing is I'm taking the n by n identity matrix, I'm removing the ith column, and I'm not putting b. What am I putting in there? Okay, so that's key. So I can write this as A times, let's express this matrix I sub I of x, right? It'll start with E sub 1, and then so on and so forth. Eventually, I'm just going to have the vector x in there, generally speaking. Okay? And then when we were doing the definition of matrix multiplication, then I can actually say this is A times E, so on and so forth. So you transform each individual one. So then A times X all the way down to A times E sub n. But think about the definition of the standard matrix, right? That definition, if I use my transformation, if I use that matrix A to transform the E1, well, that's what we meant by getting my column A1 of the matrix A, okay? So on and so forth down the line. And then, interesting, okay, A times X. What equation did we establish from the get-go that we were actually trying to solve? X is equal to B. Okay, so I'm allowed to make the step and put B in here because I'm not citing something or doing something that hasn't been previously declared. Okay? And then lastly here, A all the way down to A sub n. But this is mighty suspicious. We just kind of wrote something that was exactly like this. This sure looks like, I don't know, the matrix A, and we've replaced one of the columns with another vector, which definitionally is kind of the whole entire, first thing that we wrote on the board, right? This is just taking my matrix A, replacing that, general ith column with which vector? B. Okay. So you should not feel like you should have been able to know that this was the first logical step, okay? This right here is a non-trivial step. This is why professional mathematicians exist, because they cry for 6 months and try to figure out what these insights are so they can publish them and then demonstrate that it actually works out, and then you just have to learn it. So you can benefit from the suffering of the people who don't get credit for anything, okay? But then, notice how nicely this falls out. So I've got a product of two matrices being equal to a matrix, all with this really handy notation with the new definition, okay? So that's going to become helpful. We continue on. And if you haven't watched 3.2 yet, please do that soon, because the rest of the proof kind of entails you're familiar with those properties here. So what I'm going to do in my proof, I could immediately go into the computation, but I want my computation to be clear what I'm actually citing. So we use, what am I using, Scott? The multiplicative property. Multiplicative property. Why might I use the multiplicative property? Well, maybe because my two matrices over there, they're multiplied together. And then specifically, I'm eventually aiming for this formula, right? So specifically, the multiplicative property of determinants to show here's some more proof language. Show that we use with a citation. So really, when I think about it, this equation is saying A times I sub I of x is equal to this. So I'll start with that. I've got A times I sub I of x is equal to A sub I of b. Okay, so that's what we were able to show over here. What does this actually imply? So if I use my multiplicative property, I'm going to take, oh, by the way, a double struck right arrow means that this statement logically implies whatever comes after it, okay? So it's kind of like a domino chain. That's going to imply, so I'm going to take the determinant of both sides. Determinant of, so I'm going to take, here's I sub I of x is equal to the determinant of A sub I of b. So I take the determinant of both sides, that's all I've done. But the property is telling me that if I've multiplied two matrices together, then I can actually take the determinant of A separately and multiply the determinant of the second one. So this logically implies, through that property, that I can take the determinant of A separate. So compute that first and think of this number, and then multiply that by the determinant of I sub I of x separate. and that's still equal to my determinant, a sub I of b. Okay, now let's think. What is this determinant? There was one property that we really talked about and drove home on, I think it was Monday. If I had, diagonal entries, so the identity matrix is kind of like the obvious, handy-dandy example if you want to think of a matrix that you can just take the determinant. In general now, think about just a regular identity matrix. If I want to take the determinant of it, it's obviously already in echelon form. And so I just need to multiply down the diagonal, which conveniently for identity is all just ones, okay? So what's it always going to be? The determinant of identity is always 1. What's the only thing that's been modified here? X, okay? So that means that the one entry of the vector column X that happens to be potentially not 1, that's falling on the diagonal, is just going to be 1 times 1 times 1 times 1 times that one not, from the X. And it's going to be specifically in the row corresponding to which one it's been substituted, okay? So that's how I know that what I'm really doing is I'm taking my determinant A and multiplying it by the entry xi, because that entry xi is the only thing that survives on your main diagonal in the identity. So if you want to really prove this for yourself, you can. I may, after erasing this, illustrate what I'm talking about more explicitly. Actually, I'll just do it because I want to teach you guys. Okay, so here's an example identity matrix, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. This is an unaffected identity. This is I. If I wanted to take the determinant, I'm going to march down the diagonal. So I'm multiplying 1 times 1 times 1. Now I'm going to alter my I sub I, and I'm going to put something in the ith column. So say I put something in like the second column. So I have 1, 0, 0, and now I'm going to insert a vector x. x1, x2, x3, and then 0, 0, 1. Okay, well, basically, when you row reduce this, it's still going to slash down, and you're going to end up with your corresponding row with I. So this is xi, and determinant a sub I of b. And by the time you get to here, you've technically proven the theorem. But if you want to make it look the same as the formula, this is just a scalar. This is also going to be just a scalar. So xi is equal to the determinant of a sub I b over the determinant of a. Now, whenever you see a fraction in a proof, your brain should go, well, dividing by 0 could be a problem. Have we broken any rules? Can the determinant of a ever be 0 in an invertible matrix situation? No, we've circumvented that. So we should probably include that in a proof to show to the reader that we haven't accidentally made a logical mistake by overlooking something, okay? So we can state, because remember, at the beginning, I called it invertible. So I can say, since A is invertible, the determinant of A can never be equal to 0. It's impossible. Because that's kind of a previous theorem, was that if you're a non-zero determinant, then you're invertible, and it goes both ways. So since A is invertible, the determinant of A is non-zero, period. That's all you need to say about it. That's just clarifying that you're never going to divide by 0, so this formula is good.
It's not zero.
Not zero.
Equals 0.
That says equals 0.
Did I typo myself?
You did.
Since A is invertible.
So
Thank
you
you.
need to put a slash through it.
Thank you. Okay. Does the rule of the formula itself make sense? Oh, I thought that was a question. Okay. Do we see the elements of the proof language? All the lets are happening up here. I'm defining all the stuff. I'm using loaded math vocabulary, which is going to come with stuff for you computer science people. When you import a Java package, for example, you get a whole bunch of different things. If I import a class and I want to use its methods, all those methods come with the class, okay? So use that math vocabulary. Think of it as these classes that are coming with all these stuff that comes with it. Why does it come with it? Because that's what it means, okay? So it's a very nice Very, very nice way of thinking, because then all I have to do is, typically this is where the paid mathematician comes in, has a stroke of genius, and figures out the trick, so that when you follow your algebra rules and make a few clever observations, you can generate the formula you want. Okay? All right, questions about this theorem, Cramer's rule, anything?
So for 3.2, the rule of, I forgot the exact wording, but like when you like switch like row R1 or R3, it makes it negative. So why does it make it negative if you kept it on like the same, like if it's odd, if you flip the odd with the odd, why would you need to make the determinant negative if it stayed in the same like negative, 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 or positive, positive, positive?
Okay, so you're asking why, if I interchange two rows in a row echelon, like so if I'm doing row reduction and I interchange two rows, why it throws a minus sign out front?
Yes, if it stayed in like if you took R2 and you just row reduce, you interchange with R4, why do you need to add a negative if it's still positive through the like floppy thing?
It's not even, so we don't care about the actual values in the row. It's just the very act of making that swap of those rows causes the determinant to switch sign. The proof of which is in the text, but would take me far longer than I'd want to take in class time to cover. So if you're interested, the proof is definitely in there. It'll answer that question more thoroughly than I can right now. Okay. Let's do an example so you learn how to compute with this, okay? For all intents and purposes, this is actually a super inefficient formula for large sizes of matrices. So hopefully your homework is not horrible. I don't think there are any 7x7s or anything like that. But here's my guess. If you do get large-sized matrices, there is a very decent chance that you shouldn't reach for your calculator, and there are probably ones that break down super easy with clever cofactors, okay? So if you do get large matrices, don't freak out. Just look out to see if the problem has been designed in a way that you can quickly break down the big determinants with clever like cofactor expansion, okay? I really like this new font. I think I'm going to stick with it for the rest of the semester. It's more readable than my other handwriting. Okay, so example, let's use Cramer's rule to solve the system. So let's solve a system. For the purpose of the class, doing a 2x2 is going to be sufficient. And then minus 5x1. Oh. Alright, so minus 5x1. Okay. Plus 4x2 is equal to 8. Okay. So when I do Cramer's rule and I do plug and chug, basically assemble your ingredients and just do it. So I know that I will need for every single xi in my solution the determinant of A. So I'll need that regardless. So let's figure out what that A is in the first place. So my A here is what?
3, -5, vertical.
Yeah, 3 minus 5 minus 2, 4. So I just take the coefficients, not to be confused with the augmented. So don't make an augmented matrix here. We're making a matrix equation, so be thinking of the AX is equal to B. So then what's my B?
6, 8.
Okay. Now, we are in R what? 2. We're in R2. So my solution, x in R2, can be represented as x is equal to what? X1, X2. So that's a good thing. Just know how many of these that you're actually anticipating solving for, because you could accidentally psych yourself out and be looking for an x sub I that doesn't exist. So don't do that. No, it's only as many as the dimensions that you have for your system. And then now I think, okay, in my formula, I need to anticipate having these a sub I of b. So let's actually figure out what those are. So my a sub, what's the first I value?
1.
Yeah, always start at 1 of my b vector. Okay, so what do I actually do to my original matrix A?
Replace
B
column one
into
with
D.
Yeah, I'm going to replace the first column of A with the vector b. So here's my vector b, and it needs to go in the spot of the first column, 6, 8. Do I modify anything else? No, everything's exactly the same, so minus 2 and 4. Okay? And then what about a sub 2 of b, right? Because I need to get all of my a sub i's.
You put B in column 2.
Yeah, put b in column 2. Do I change anything else?
Nah.
No. Okay, so we have 3 and minus 5 in the first column, and then now I'm putting the 6 and the 8. So I'll put a little dotted line underneath those so you can kind of see what's been changed out. Okay, now why did we make these?
So we can solve
Just
the
take the
determinant of them.
Yeah. Is it the matrix itself that's being plugged into the formula? No, it's the determinants. So let's compute all 3 of these determinants, and then we'll be set to plug and check. Okay? So the determinant of just A with no modifications is what?
12 minus 7.
Yeah, so 3 times 4 is 12, and then minus 10. So that one's 2. And then my determinant of A sub 1 of B, here's my A sub 1 of B. 6 times 4, 24. I subtract away negative 16. So then I'm really adding. So 2 plus 1, 3, 40. And then my determinant of A sub 2b, I look over to my A sub 2b and I think, okay, so 3 times 8 is 24.
18 plus 30.
Okay. And then minus 6 times minus 5 is negative 30, so negative 30. Minus a minus, 2 plus 3 is 5, so 54. Fantastic. Okay, so Cramer's rule tells me that x1 is equal to what?
Determinant A1 of B divided by determinant of A.
Okay, so what is determinant A sub 1 of B? Well, yeah, A sub 1 here is 40. And I'm dividing it by my determinant of A. So that is 20. X sub 2. Okay, so for x sub 2 in the formula, I need the determinant of A sub 2 of B. So determinant A sub 2 of B is 54. And that's still the same denominator. And that's 27. So here's what you don't want to do. You don't want to do all of this work correctly and then forget to actually just answer the question, okay? So format it as a vector. It asks for a vector solution, give it as a vector. Don't leave it in its separate components. So I'm putting in a vector x is equal to 20, 27 as a 2 by 1. So this is considered the solution. So without that, you're technically incomplete, okay? All right, does stripping out the A from the coefficients make sense? Does identifying the B from basically the other side make sense? Okay. Does it make sense why I know I'm really only looking for an x1 and an x2 and that's it? Okay. Does it make sense how I then go and systematically list out all of my necessary A sub i's, right? So A sub 1 and A sub 2 in this case. Does it make sense how to perform the determinant computation for this example? And does it make sense how I'm choosing, how I know exactly which one of these determinants I'm dividing by the determinant of A for each corresponding x? And then you just write your vector. If this was a 5 by 5 system of equations, okay, so my A would be 5 by 5, my B would be 5 by 1. How many x components would I be looking for? So I would be performing that formula 5 times. Meaning that how many of these A sub i's would I be needing to make? I need 5 of them. And then you need to compute the determinant of A, the determinant of all 5 of those, and then it's the same. Okay? Yeah. Great. Questions? Concerns?
I have a concern.
Okay.
Can you do like a 10 by 10 on the test just for me?
Okay, here's how I'll say it. There will never be an ugly brute force test question because what's the point in an ugly brute force test question? If it's going to be big, there's going to be an insight and a pattern that's going to make it solved like that, okay? So I prefer math questions that are hard to get to an insight, but the second you see the insight, it's like a 10-second solution, okay? That's the kind of problem I like. Either that or just base, did you know the definition? Can you do the operation? That's what the other thing is, okay? All right, so there are some other relatively unimportant things in this section, but it's still worth talking about because you paid for the class. But this is the highlight of the section, Cramer's rule, okay? This is really the big one. And this actually, it might be kind of fun if you've taken Calculus 3 to see some of this transformation language used in the theorems. Because it generalizes nice, but yeah, that is what it is. Okay, there is a direct formula that we can get for inverses based off of Cramer's rule, actually. So I'll give that to you so that you know what it is. You may need to do it for your homework too, so there's that. The IJ cofactors, that's a math word. If you forgot exactly what an IJ cofactor is, go back in the notes, make sure you review that definition. Cij of an n by n matrix. It needs to be invertible, so let's state that. Invertible matrix A. V, and that's kind of a funny word, adjugate, which is sometimes also called the classical adjoint. But the adjoint language is going to be used in a broader context, so honestly, I prefer adjugate for this class. Of A is, and then there's this kind of whole ugly thing, okay? So ADJ, adjugate of A, is equal to C11, C12. So down this, way it's going to work is we're going to fix that as 1 all the way down, and the second index is going to increase to n, so 1n. And then as we move across, then the first index increments up by 1. So now with C2, we start at 1 again, and then the other indexing pattern vertically is the same, so that'll repeat itself, so this will be 2 and n. So that's going to continue, that's going to continue, and we end up at n, the nth column, and then we're at the bottom, obviously, with everybody's favorite news network. Okay. Oh, I forgot. That's bugging me. And if you wanted to be really overdoing it, actually no, it looks terrible.
That's a lot.
It's a lot. Okay, so every single one of these capital C sub something something is an IJ cofactor. Okay, so recall that an IJ cofactor, Cij, actually has an explicit definition from, I think we actually talked about that on Monday, yeah? Pretty sure. Do you guys have that? You remember it from your notes?
Oh, you delete
The alternating component, I plus j.
-1 to the I plus j
Yeah.
determinant Aij.
Good. So this is going on in every single one of those entries. Is that horrible? Yes. Can you make a computer program do this so that you don't have to? Also, yes. So if you ever need to generate by formula, by direct computation formula, a inverse of an invertible matrix, that technically works out for you. You're never going to run into issues with breaking the laws of arithmetic because, again, determinants are not going to be equal to 0. So you're never going to be dividing by 0 or anything like that. Should you really memorize that? Honestly, no. It's more efficient to use the inverse algorithm that we did where you row reduce and you have both of them kind of like mirrored side by side, and after you reduce the matrix A to the identity, then you have the inverse right there. So honestly, that's way easier than this. The only case where I could see this being more practical by hand is if you have lots of void entries in matrices. So if you have large matrices that have tons of zeros in it, so that most of the determinants are going to just blast away, sure, it could be pretty fast to mentally just check all the cofactors, but either way, it's a new tool. You can use it. And then the formula for the inverse itself is I can take A inverse to be 1 over the determinant of A times the adjugate of A. Actually, it's really funny. So remember when we did the formula for the inverse of a 2 by 2 matrix? That's coming from this. Because the adjugate of A, when A is only 2 by 2, it's really easy to just do your cute little C11, C12, C21, C22. And then it was 1 over the determinant. So there's that. Okay. Questions about the notation of adjugate? Questions about the IJ cofactor notation? The formula itself? Cool. All right, so let's finish up then with 3 little things. And this is now going to pertain to the application of using determinants for volumes and areas. And we'll call back our lovely parallelogram rule. Sometimes in the math section, I like to think of these theorems as the textbook writer has an obligatory section to justify the existence of other concepts that he taught in the book that honestly don't come up that much, except for you can convolutedly make it apply to this current section. So it's application, yes, but taught in better context in other sections probably. Okay. If A, and actually the main thing that I want you to learn out of this is a tip for reading math books in general. Okay, the way that this is going to be constructed, read by analog. So after you read the first one, when you read the second one, you should be kind of mentally filling in the logical equivalency of how it's being constructed as a theorem. So if A is a 2 by 2 matrix, the area of the parallelogram determined by the columns of A. Because remember, the columns of A can be just viewed as vectors. Is the absolute value of the determinant. The reason it's absolute value is because there's no such thing as like a negative area. That doesn't make sense. So we want to make sure it's actually positive. Okay, so what they're going to do is do an analog into 3 by 3. So I'm going to show you these parallel components of construction. If A is a 3 by 3 matrix, okay, so that's the first thing, right? Stating its dimensions. What's the analog to area? Volume. Of the, now I don't know the term, you might not know off the top of your head, but you like mentally have an idea, right? So basically, whatever the term is for the 3D analog of a parallelogram, so we call it pipette. Determined by what?
The columns of A.
Gee, how did you know that?
The other one.
Yeah, and it's all analog. By the columns of A is, my goodness, can we speculate a little bit?
The absolute value of the
No way, Sam Patchen, how did you know that?
Wild shot in the dark.
That's crazy.
He read the book.
Genius level, honestly. Someone call Feynman. Okay, so, if you ever pursue higher degrees in STEM, knowing how to mentally extrapolate like this will save you big time. It's kind of the only way to keep up with the pace of grad school, is you get to the point where you understand a base concept and then as much as possible try to extrapolate the logic of it into other things. Because then you're going to naturally be motivating the right questions to be asking as you read through a text. And then suddenly, when they give you like a little warning box or a theorem that counters something that your intuition thought, suddenly that has a lot more meaning to you as a learner. Because you're thinking, the reason this is important is because if I was following typical intuition, I would reach a wrong conclusion. Okay? So sometimes that does happen. Math isn't always exactly analog and intuitive, but those things are much easier to memorize when you're thinking of them together. Okay, so there's another theorem that's going to be constructed in another analog sense. So let, I love that word, T R2 to R2 be the linear transformation determined by, okay, what dimensions does this information give me about the matrix dimensions? It's a 2 by 2, so a 2 by 2 matrix. We can call it A. Then, if I have S is a parallelogram in the plane, then basically what happens is, suppose I want to take this parallelogram and then transform it using this transformation T. So then the result is going to produce a new shape, an entirely different shape. And the area of this new shape, so the area, I can't spell, okay, A-R-E-A, area of the transformed space, okay, so whatever the resulting shape is, well, our lovely absolute value of determinants coming back for a cameo. Gee, I wonder why that might potentially be related if I'm talking about areas of involving a parallelogram. It's kind of crazy. Times, and then the original area of S. Okay. So then the analog, let's construct the analog. If I have a transformation T, and instead of, let's do with a 3 by 3 version, so it'll be R3 to R3. Be the linear transformation determined by what?
3 by 3, yeah,
3 by 3.
By A. How do we know that? Oh goodness, I don't know.
Holy
intuition, one might even say. Then, if S is a, now again, you might not know the exact jargon terminology, but mentally you can think, okay, whatever the 3D version is of a parallelogram, right?
The parallel pipe.
If S is a parallel. In what?
R3.
How did we know it was R3?
Just the in.
Because we're on 3 dimension. Yep. Maybe that's why people think I'm like give dry sarcastic answers. It's really not sarcastic. I don't mean to be. I just have been studying math for too long, where they say really obvious stuff all the time. Okay.
The volume of T is.
Gee, how do we know it was volume?
Curly bracket equals determine a curly bracket volume of S.
And again, all of this by analog. Okay, so does this give you a taste of how to read math? Because I know I get on you for reading the textbook, so I might as well actually help you learn how to read a textbook beyond just, this is painful and not fun.
That's exactly the sound I did.
Okay, now, even further, when you read a math textbook, after you read a result or a theorem, the question that should pop into your brain almost immediately is, I wonder if I can generalize that. That's got to be abstractable. That's got to be general somehow. And then either find a way, make a way, or realize that the way can't exist, okay? So, especially with this transformation stuff, why might this become really useful? Well, not everything that you build is in a parallelogram shape, okay? But, gee, wouldn't it be so conveniently fantastic if I could take any general finite closed region in R2 in the plane, and then have it so that if I transform it with a linear transformation, then the resulting area of that new transformed region still follows this exact same analogous behavior. Fun fact, it does, okay? So that's how you can generate, if people think of linear equations and they only think of lines and straight boxes and things like that, you can prove and generate the formula for the area of an ellipse by knowing how you modify a circle in the plane from a linear transformation. It's going to be the same thing. So this extends itself, and if it extends itself for finite regions in the plane, by golly, it's going to extend itself in finite volumes in space. Okay, so that's 3.3. It's the rest. That's the end of chapter 3 for this class. Watch 4.1 when it gets uploaded. I will post a D2L news item when it does get uploaded, so you don't have to guess when it's uploaded. Any questions? Cool. Oh wait, yeah.
What would you do if you were in 4 dimensions?
Yeah.
Yeah, a 4-dimensional parallelogram.
Counter question. What do you already know the answer is going to be?
Determine A.
Determine of the columns of A. The question